recorded, and that by staying in the meeting, y'all agreed to being a part of the recording. And with that out of the way, feel free to put questions in the Zoom chat or the appropriate thread in the Ask a Teacher channel in Slack, and we'll try to get to them near the end of the meeting. Okay, so our speaker is Ankit Ramchandani, who is going to be, who's currently researching deep learning to predict the spread of COVID-19 in the US using several heterogeneous features. He has also interned at Facebook in an applied machine learning team to create models to rank Facebook stories, and researched in autonomous driving and detected lane marks and traffic signs using machine learning. So Ankit, thank you so much for taking your time to do this today, and feel free to get started in your presentation.
Sure. Thank you for that introduction, Felicia. So let me share my screen so we can get started. Okay, so we'll be talking, as you know, probably about convolutional neural networks and semantic segmentation. So let's start. And let's start with the outline basically. So I'll start by giving you a background of like the image classification problem and motivating an operation like convolution, like why maybe it's not something else. And then we'll just straight dive into CNNs, convolutional neural networks. We'll talk about the convolutional operation. We'll do some demo. We'll talk about the convolution and the pooling layer. These are two layers which are useful in the network. And we'll talk about like a nice architecture, which could be useful for your future projects or something like that. And we'll briefly talk about semantic segmentation. And depending on the time, we can get into more details into that. And we also have a demo for you. So let's get started. So let's build some background. So for the image classification problem, as you can see, guess from the name, it basically refers to classifying an image with what is in the image, basically. So like, for example, in this image, you say there is a baby in the image or a toddler. And I want to motivate the need for machine learning in such a problem, because you might think, why not like just regular computer programming, or why not a different paradigm? Why would that not work? Why do we need learning? And that is because, think about this, how do you teach a computer how to recognize a toddler? Maybe you'll say it's like she has a small face, maybe like, and when you say face, you have to define what a face means. So like face has eyes and nose and mouth, and you need more specific definitions of those things, but let's stop there. Maybe you say a face, a small body, and like eyes, mouth, nose is what a face means. And then you see this image, and this toddler has a face, but the eyes are not clear. So your model, which with whatever definition of you set for your eyes, will not classify this as a baby. So that'll fail. But now maybe you say, maybe I'll try a different idea. Maybe I'll try saying that a baby is like a small human being with some ordering of parts, like the head is at the topmost part, the body is next, the arms, and the legs, and then you see this image, and then your rule fails there again. So the big point is that you cannot come up with a good rule to tell me which will classify all these images correctly. And these are just 3 images, and it's pretty hard to just come with a more standardized rule for just these 3 images. And when you have millions of images and many, many different classes, this is just one class, which is the baby or toddler, you'll see how problematic that is. But if you say want to classify a cat, you have to go back to the drawing board and say, what does a cat have? Like a face or like whatever, you see? So we need some mechanism of automatic learning. You show the images to the computer, and it can tell by itself what is in the image and what makes a baby a baby. And that's where this kind of entire field starts of machine learning. And then, I mean, we are talking about like a more advanced version, which is the convolutional networks. It's subfield, but that's where that's where the need for learning begins. And before I talk about how to solve such a problem, which will require learning on images, let's talk about how to represent images. And images, well, color images at least, are represented by 3 channels of red, green, and blue. And what this basically means is that every color can be represented by some intensity of red, some intensity of green, and some intensity of blue. And the combination of these 3 intensities can make any color, basically. And that's the principle these images are made. So here you can see, if I get my laser pointer, you'll see that there are like 3 channels. The first, this
will
is
be used for planning for the start of the fast material.
Sorry, what's your question? Okay, maybe not. So let's, I'm looking at like one portion of the image here, and that's like a 3 by 3 square. And you can see that there are 3 channels. So red, green, and blue. And each channel has value from 0 to 255. 0 means low intensity. So less red is 0 if red channel has 0, and high is close to 255. So 243 is high red, and 43 is maybe low green. And if there is a grayscale image, the size will, there will be only one channel, which will tell you the intensity of that, of how white the image is. 255 is white, 0 is black. And more formally, the shape of this image, or the structure, the data structure of this image, is a 3D tensor. And a 3D tensor, you can think about a 3D tensor is to a matrix what a matrix is to a vector. A vector is just a one-dimensional set of elements, right? And the shape of the image, or this tensor, is 3 cross h cross w. H is the height, w is the width, and 3 are the 3 channels. And if you have more channels in some different form of image, then that will be that number there, like c cross h cross w, where c is the number of channels. And now let's think about how will humans do it, or like let's try to think about what you will think of when you try to classify an image, and you want to say this is a toddler. So I think for first few things that you look at, or like implicitly at least, are the edges in the image, or the contours. What distinguishes the boundary of one object from the other? And once you do that, then you know what objects are there. And I've done some image processing, like just conventional image processing, no machine learning here, and gotten out the edges in this image. And you can see this is like a pretty good estimate. Like just by the edges, you can tell this is a toddler, right? Facing upside down. And what really are edges? To be more formal, edges are just prominent, noticeable changes of intensity in local regions, right? So if I go back to this image, so this is an edge because this the intensity here was white, and or the color is white rather, and then here it changes to like the skin color, and that's like a marked change in intensity, and that's what is an edge, right? And you want to define, and you want to, what this like shows is that you want a method that does some sort of local processing instead of global processing, because edges are like very local properties of images. Like you can apply the same method locally and everywhere in the image for all small regions, and you can still find the edge. Like if you check for changes in intensity, you can check it everywhere, and that method is not like a global method; it's a local method, because you're checking like local a locality of the image, a small locality. And for those of you who have a background in like deep learning a little bit, this is just one. There are many other reasons. One reason that fully connected neural networks will not work on images, because they kind of in some sense look at the image in a more global fashion, where local processing would be better. And this is again just one reason. There are many other reasons why fully connected networks or fully connected layers will not work. And so let's take some inspiration from the image processing community and see if they've developed an operation which can do this sort of local processing. And that operation is the convolution operation, without surprise, right? And what is the convolution operation? So basically, it needs input, which will be the image. That's what it will be applied on, and it needs a kernel, which are in some sense you can think of as parameters of the operation. And in this case, I'm using like a 3 by 3 kernel with some weights here. You can make those weights anything you want, but basically, when you want to apply, if you want to apply this kernel to this grayscale image, then you'll basically do a weighted linear combination of all spatial. I'll just show you one example. That'll be easier than defining it. So you take this region of the image, this 3 by 3 square, and you put this kernel on top here, and then you multiply, for example, 123 times 0.06, and add plus 41 times 0.09, plus 19 times 0.03, and so on and so forth. You get one number. You take that one number, and that number will basically be the first pixel in the output. So if this is your output, then this value will be the weighted sum of that kernel on that space. And then you can do this, and you can now shift one pixel, and then you can do this again, right? You can take this rectangle, and then you compute the same weighted linear combination. So 0.6 times 41 plus 0.9 plus 19, and so on and so forth. And that sum is going to be this number. What I want you to note is, I mean, we'll talk about this in much more detail, but first note that this is a local operation, and this can be very well used to compute differences in image intensity. Like, this can be used very well to find out the edges of images. And I'll show you exactly how, but I want you to just note that the first image that I showed you here, this was done by, found out by some convolution kernel. And we'll talk about that kernel in a bit. And this is like an animated version if what I said was a little unclear. So in this case, the weights are the bottom right-hand corner, numbers in the bottom right-hand corner, which are 0, 1, 2, 2, 2, 0, and the image is the blue grid, right? And when you do the convolution, so I want to like pause the animation here just so that it's more clear. When you multiply 3 with 0, you multiply 3 with 1, and you add 3 with 1, add the product of 3 and 1 plus the product of 2 and 2, and so on and so forth. You do everything, and you should get 12. And you do this here, and you get 12 again, maybe. And you do this here, you get 17, whatever. Basically, it's a weighted linear combination based on the weights set in the kernel for overall possible location of the image. And even if that is not clear, then I have one more animation for you. It's this. So this is what I meant. Like the kernel here is like that shade, the shadowy region, and the output is being computed the way you see it is being computed. Basically, the weighted linear combination, the sum, the weighted linear combination of that region with the weights set in the kernel, and then you just create the output. The note here, the output is smaller than the input. The dimensions of the output, like the height and the width, are smaller than the input, and that's because there are some regions. If I go back, there you cannot do a convolution, or you can, but I'm not doing it here. Maybe on something like this region, or this rather, since we're on 3 by 3. This region. So because there are no more entries here. I mean, you can pad entries and you can make that happen and maintain the same spatial dimensions if you want, but in general, if you don't do something special, then it won't happen. So I want to pause for just a minute here to check if there are questions, because this is like an important definition and will kind of set the tone for the entire rest of the talk. So just like a few seconds to see if there are questions, or if the definition is clear. We'll also do a demo, so it'll be clearer. Okay.
I think there's one question, like
yes.
John is asking, how are the weights determined?
Right. So that's where learning comes in, right? So the weights here, I just set them to random values here, but when you put it in a neural network, when you make it a layer, this is just an operation, not a layer in the network. But once you make it a layer, we'll see how like the lower weights are just learned by backpropagation there. And though we'll not touch upon the details of backpropagation, because that isn't like a topic in itself, but if you have the background, you can see like it is just basically gradient descent. But like, the big picture here is they're learned. That's what matters. They're not set by any human being before. They're learned based on the data. Are there any other questions? I somehow cannot see the chat because I'm nothing sharing my screen. Maybe you can tell me, Felicia, if there are more questions.
No, I think that's it for now.
Cool. Okay, so this is like the vanilla convolution in some sense. And there are few more concepts. I talked about padding. So padding can be used to like increase or maintain the spatial size of the output, and not have it reduced. I mean, some applications that might be useful. The other concept is that of a stride. What is a stride? Well, if you see here, if you go back to the original example, what I showed you first was that we will first take this region of the input space, and then we'll take the next region. We'll just move one pixel to the right here. right? But you don't have to take 1 pixel, move 1 pixel to the right. That is an arbitrary choice, right? That I just made. You can move 2 pixels to the right, and that things will work. I mean, there will be a side effect, of course, that the output dimensions will be even smaller, but things will still work. I mean, convolution is still defined if you move two steps to the right, and even 3 steps or n steps to the right. And that the number of steps that you decide to move right is what is called the stride. So whatever I was showing you and what all the graphics were, or all the GIFs were showing you, were stride 1 convolutions, and 3 by 3 stride 1 convolutions. So 3 by 3 is I'm talking about the dimensions of the kernel here, right? So you can see the shadow region is 3 by 3. So that's 3 by 3. And this goes back to the motivation, right? We wanted some operation which is applied in a more generalizable way, but on a local area. This is that operation. It is applied in a local area, right? And I want you to note that this is an equivariant operation. What does equivariant mean? So think about this. Let's go back to the slides. Let's say when you want to classify a baby, you really don't care if the baby is really here or maybe here. I mean, the baby can be anywhere in the image. You still want to find out if there is a baby or not. So if you move this image, like maybe this image, 1 pixel to the right, it's still the image of a baby, right? And we want, ideally at least, an operation which is used in a neural network, which is learned, the parameters of which are learned, to be more specific, which can respect this fact that the very translation, any change in translation doesn't change to the output too much. And this is convolution, in some sense, does that, and that's why I call it equivariant. So let's think about this. Why? Let's say you move this image 1 pixel to the right. What will happen? Well, basically, this region, this column will be deleted, and you have one more column on the left, which you'll have to fill with some values. I mean, let's just say 0. Right? So, I mean, I'm maintaining the spatial size of the image. I'm not reducing, I'm just not throwing that column away and starting over, right? But when you do convolution over here, or convolution with this new image, what you will first compute a convolution over this region, and then you'll go here, right? Now notice that this region, the region in green was already done in the previous image, right? The one in which the image was not shifted to the right. And you will do this here again, and you'll keep doing so. Or well, you'll not do the last one because you delete the row. But what you see is there's only one new convolution operation which is being added, or one new convolution that you're doing, but everything else has been done before, right? Because everything else has been computed here. Because you know, for this green square, which was green before, now it's not, the value of the convolution was 12. So the output, when you shift the image to 1 pixel to the right, will also be shifted 1 pixel to the right, except like again, so this row will be deleted in the output because this row is deleted, and there will be a new row added, and this row will have some new different values, but overall it will just be shifted 1 pixel to the right. And that's why this is equivariant, and this holds if I change the direction of translation. If I move downward, that happens too. If I move upward, that happens too. Hopefully it's not too difficult to see. And the other thing to note is like, this is a linear operation, and this becomes important when you do some sort of learning, because if you just keep 10 convolutions, just do 10 convolutions, and you learn the weights by backpropagation or any other method, the result will still be a linear operation because you're just doing a linear operation 10 times. So the representational power of your model will be pretty low. It's just be linear, right? Which is usually not enough for real world applications. So let's take a break here and look at convolutions a little more in detail before we go into the next slides. And this is when, Felicia, you can share the link in the chat. And so I made this Google Notebook for you where you can basically give any images on the input, any images as input, and define a kernel of your choice here, and I will return the output. I'll do the convolution for you. I mean, the program will do the convolution and return the output, and you can see. So let's do something here. Let's run this. Again, if there are questions, please interrupt me. I cannot see the questions because I'm, I think, sharing screen, or maybe I'm not that good with this. So let's do it in 2 images and see what happens. And so the filter that I'm currently using is this. So let me show you. Okay, so the filter I was using there was once everywhere and multiplied by 1/9. So let's say equally weighted, equally weighting every element in the kernel. What does that do? If you notice now, the left is the input, the right is the output here. If you just let me make this a little bigger. If you notice, the image has become like a little more blurry. So you can see in this case, the eyes of the cat are maybe it's easier to see here. So the edges of the boat here are very sharp, but here they're not as sharp. They're kind of quite dull. Similarly, you can see the clouds, the boundaries of the clouds are really sharp here, but it's not in this case. Even in the edges here will be sharper in this case. They're not here, they're kind of blurred. And why does that happen? So let's think about this. Yeah. So here, if you do that operation here, what I'm basically doing is I'm taking an average, right? I'm taking an average of all these elements and replacing that average number as the first element in the output, or the corresponding location, right? I'm doing an average here, and I'll put the average here, and I'll put the result here. That's why the weights are 1/9. What averaging a local region of pixels does is basically it takes off it removes in some sense all the sharp details in the image, because if the image is, if you think about how an edge will look like, an edge in the image, if it's a vertical edge, let's say, it will be like high intensity here, excuse my handwriting, but it's 255, 255, 255, and then 0, 0, 0 maybe, and 0, 0, 0. This is a strong edge, right? It's the best edge you want because it's all black and then it's white here. But if you average this kernel, my PowerPoint is not okay. So if you take an average if you average this value, average this space rather, then you'll basically get 255 times 3/9. So 255/3 everywhere in some sense. And that you can see will reduce the sharpness of the boundary, right? Because it's 255/3 is everywhere. Does that make sense? Let me know if there are questions, basically. But hopefully it's clear, kind of. So let's try some other kernel. So let's remove this and let's try a more fancier kernel to see if I can find edges in the image, or edges of particular orientation. And this, you can, if you want, you can put in the chat what other kernel you want me to use. I can show you some other kernels. You can put the links of other images you want to see the results applied on, and I'll put that. But let's see what happens here. So you see, if I use this kernel, which is -1, 0, 1, -2, and so on, you'll kind of get all the vertical edges, which are dark. Let me see if I'm saying this right. So yeah, which go from in which the intensity changes from dark to light. So in this case, in this region, this area of the cat, her fur is kind of black and the background is white, so it's a dark to light edge. And you can see this has been picked up very well here. Why is that the case? Well, what does dark to light mean? Dark to light is this edge, right? So 255, 255, 255. This is, I mean, this is the extreme example, of course, but a very bright edge, or very bright vertical line, and a very dark vertical line. That makes it an edge. And if you apply such a filter here, what will you get? If you apply this filter like just on this, exactly on top of this, so you will do 255 times 1, right? 255 is here, and this gets multiplied by 1. Then you do 255 times 2, or you add 255 plus 2, and you add 255 plus 1 again. And then you subtract 0 times minus 1, 0 times minus 2, and 0 times 1. And the middle values are 0. So that doesn't matter. And the response will be very high, right? Because it's, I mean, ideally, if I want to make things easier, I should divide this by the sum of the kernel. I'm not doing this here, but this, it'll be done automatically. Because I mean, the maximum value is 255. So if my average is over 255, the computer will just read this from 255. You cannot get more than 255. So basically, you can see that that number will be kind of quite bright, quite high. And that's how you detect all the edges from dark to light. And if you want to switch the direction of dark to light, so you want to detect light to dark, then you just negate the kernel. And hopefully I can show you how that happens. So you see now this time, this edge has been detected, not this edge, right? I mean, when I say detection, detection means if on the right side the image is brighter, that's kind of detection, or the signal is high, right? So now you're going from light to dark. So then light to dark is detected, dark to light is not. And I should have shown you this image for the previous case also, but you can see here again, so you go from light to relatively dark in this region of the image, and that has been detected very well. But when you go from dark to light here, it has not been detected that well because of the filter, right? And because that number will be negative in some sense, right? Because what you will be doing in a dark to light scenario will be this. Let me go to the next slide. It'll be 255, 255, 255, and 0, 0, 0, 0, 0, 0. That's how light to dark looks like, right? High intensity and then low intensity. But when you apply convolution over this, what happens? Or you apply this kernel over this, then you do 1 times 255, like same thing that we did previously, basically, and you detect the dark to light. But if you do the other way, if the 255s were here and zeros were there, then you can see the number will be negative, right? Because you'll be doing -1 times 255 plus -2 times 255 and so on. So that's why that will be detected. The big point, however, is that convolution is a powerful operation that can be used to detect edges, among other things. I mean, I showed you that it can also blur images. Like, I mean, there are other kernels that you can try that will sharpen images. So the point is that it can be used to detect these local changes in intensity very well, or local changes of gradient, the gradient of intensity from light to dark, dark to light, or things like those. And that's why it makes for a good operation to be used in such a learnable method. And especially if you allow the network to learn the way. So if you're giving this to a network, if the network is asked to maybe predict skyscrapers, the network can learn that detecting vertical edges is an important part of detecting skyscrapers overall. And the network can learn the weights that I've used in this example and detect the skyscrapers. So I mean, that can just be one part of the whole thing, but that's how it can detect skyscrapers. Possibly. So is that clear? If people want, I can show you more examples on different images or more kernels. If you have ideas of kernels, put them in the chat. Let me see how we're doing on time. Okay, so I'd rather not because we're kind of running short. But if there are questions, I can take a few questions quickly.
Yeah, there's a question. So
Yeah.
one of the questions is, can you change the starting point of the kernel and the direction it moves? For example, starting in the bottom right-hand corner and then moving up and to the left.
Starting from the bottom right and moving to the left. Wait, let me read the question clearly. Okay, not sure. I'm whoever asked the question can feel free to unmute yourself, like, and clarify what you really meant.
Hey, Ankit, I think I might know what they might be asking.
Yeah.
So in like graphics, we always show that the convolution kind of starts in the like top left and then iterates over all the cells like in a very like downward and to the right fashion. So they're wondering, does the order that we run the convolution over the image matter? Does that make sense?
Yes.
That's what I saw.
Right. Okay. If that's the question, it does not, right? Because however you do it, as long as you maintain, let's go to that image. As long as you maintain the fact that the output, the same elements in the input correspond to the output, it doesn't matter, right? So if you, for example, you don't want to go from left to right, and you can go right to left. But if when you start here, and the first element of the output that you build will be this element, right, on the bottom right corner, and you can do it in whatever order you want. But if as long as the associated, the mapping between the input and the output is the same, it doesn't matter. Okay, hopefully that answers the question. But if there are more questions, again, like wait after the. I mean, I don't know if that's if there are more talks. So, I mean, I can take questions at the end because we have to kind of cover a lot more material. So now we've talked about the convolution layer or convolution operation in image processing. We can now build the convolution layer in neural networks. And as I showed you before, the input image, the shape is the number of channels times the height and the width, right? And one filter, let's say one filter of the convolution, in my case, it was a 3x3 filter. The dimensions are case, so will be C, which is the number of channels, so 3, and the kernel height and the kernel width. So in my case, what I showed you before was a 2-dimensional convolution. We are extending it to 3 dimensions because you cannot apply that directly to an image because the image is 3-dimensional, right? The shape of the image is 3 cross H cross W, right? So you need something which is 3-dimensional. And you do exactly what I said for 2D, but you extend the 3rd dimension. You basically do the weighted product and not just the spatial in the 2 dimensions, but also the 3rd dimension. So instead of having the kernel size be 3x3, you have the number of channels times 3 times 3. And that's, it's just an extension, it's a 3rd dimension. And and this was just one convolution filter applied. If you want to apply multiple of them in parallel, what you can do, the shape of the filters will be n standing for the number of filters, times the size of one filter, the shape of one filter, which is C cross H, kernel height, kernel width, right? And when you apply that to the image, the output will have certain dimensions. It'll just be like, I mean, there's a relation between the output height and the image height, but it's just like arithmetic. So I'm not covering that here. But the important point is it will have the same dimensions as the input. So like just 3 dimensions, and you can treat this output as an input to the next convolution, and you can apply convolution over and over again and keep doing this. The one thing that I want to clarify here is why is the first element, why is the first element n here? Seems like my pen is not working, but why is the first element n here? The first element of the dimensions. Basically, when you apply one convolution filter, what you get is a O sub h, or output height times output width image. When you apply n filters, you would get n of these O sub h and O sub w dimensional filters, right? And basically you just then put them together and add, as in, you basically add a new dimension and just stitch them together, and then that's why it's n times O sub h times O sub w. So because the result of one convolution filter results in O sub h times O sub w dimensions. And I mean, talking about backprop will get too involved, but like someone asked how are these weights determined, but these are learned by data. So no one chooses the weights, the network learns them basically. And so this is another important type of layer which is used in convolutional neural networks, which is the pooling layer. And what this does is pretty simple. Like, it takes a rectangular region or some region in the image and then replaces the value there by a summary statistic of that region. So maybe a maximum, right? So in this case, you would take this region of the image, and then if you're doing max pooling, you basically just, and then with 3 by 3 kernel and stride 3, so you move 3 in the next move, you'll basically replace this region of the image by the maximum, which is 215, I guess. Yeah, 215. And then you replace this region by the maximum, which is 255. So 255. And this is just an easy way to reduce the spatial size of the image so that you can do more computation later on more computation later on, basically, or like you have more filters for convolution layers which will succeed the pooling layer because the spatial size is less, so you can do more computation there. The important part here is that it is a nonlinear operation, right? Unlike convolution, so it adds some sort of nonlinearity, makes the entire network learn some nonlinear function. And the other important part is that it is approximately invariant to, it has approximate invariance to small translation, which means like if this 215 was not here and maybe here, like just like that example I showed you before, when we move 1 pixel to the right, the output of this region will, when you do max pooling, will still be 215 because that is still the maximum number. So this in some sense is important in image classification because you want some sort of translation invariance, right? Because if the baby, as I said, is not on the left side of the image, but is on the right side, it still is a baby. So you want the operations to kind of implicitly understand that or capture that idea. And max pooling some sort of does that. Of course, I mean, if you, I can show you maybe an example here. So yeah, so 250 is here. If you move it 1 pixel rightward, it'll be here. Then the output of this will change, right? So it is approximately invariant, not like mathematically invariant. And as I said, it improves computational efficiency of later layers. And it can also be useful to take varying, okay, that point we'll get a little detail to discuss, and I think we're short time, so we'll skip that. But let's talk about this example architecture of BGGNet. So if you understand, if you understand convolution layers, and I mean, there's a lot more to all of this, what I've said, but if you understand convolution and pooling layers in some sense, then you can build a network based on mostly those layers, right? So you can see this is like a network, I think, which won the ImageNet competition. It's a competition where you have to classify, I think, 1 million images into some categories, and it's like a benchmark of performance in machine learning or computer vision. So this network got the first place in, I think, 2013 or 14. But what it does basically is just convolution, right? So 3 by 3 convolutions, and 64 means the number of filters, right? We talked about having multiple number of filters. So, and just a bunch of convolutions, then a pooling, and then you can see that the number of filters increase here, 128. Then you do that, you pool, and then you get 256. The number of filters keep increasing, basically. Why is that? Well, there is no reason. I mean, this is just like, I mean, there is a reason, but there is no mathematical reason that bounds you to use this design. You can get flexible with this, but the reason like many networks do that is because after you pool, the spatial size of the image reduces. So in some sense, you can do more compute and not take that much time, right? And more, or you can have more filters and not, the processing doesn't take that much time because the spatial size is smaller. So as you keep pooling, you kind of also keep increasing the depth, so, or increasing the number of filters. So, so the network can learn more interesting patterns. And then there is some form of regularity or repetition here, right? Like you see these set of three layers being repeated every time. And this is something that happens in many neural networks. More fancier architectures like ResNet also have that. I think there has been some study that if you automatically let the computer choose a neural network design, it will sometimes also takes repetitive design. So, I mean, it's like I don't know if there is a strong reason. In this case, it's like because this is designed by humans, so you don't want to like design 16 layers, or if you want to design ResNet 101 or BG or something, so you don't want to like design 101 different layers by hand. So you just like come up with a strong block and you keep repeating it over and over again. And the other note is it's only using 3x3 convolutions, which means kind of in some sense those are enough. And you don't have to use like larger kernels. And this is also again used by further networks. I think ResNet also does that. And then there are fully connected layers at the end of the thing. At the end of the network, which is here, FC means fully connected. I don't think I have time to talk about the exact details of fully connected in the presentation. I can take questions over them and describe them in detail, but they're yeah. So let's see how this connects to image classification, right? If you take such a network, how can you do image classification with it? So if you want to predict, let's say, if you want to do classification over n sub c classes, then the output dimension of the network that conventionally is used is also n sub c, or this is a vector. So when I say dimension, which means like this, the output, which is this, or oh, my pen is not working, but it's this. So then this is also n sub c, or the number of classes, or the number of elements are equal to the number of classes, and that represents a probability distribution over all classes. So it basically sums to 1. And if the first element in this case is, let's say here is 0.5, that means there is 50% probability that the image is a dog, and if this is 0.2, then 20% probably that this is cat, and do it for all layers. And you again, so since we're talking about like convolutional neural networks in particular, I cannot like unfortunately talk about the details of backprop and everything else, but for those of you who know, this is like trained by cross entropy, which is like a loss function used to train classification problems.
Hey Ankit, we're at about 5 minutes until the Q&A portion.
Sure. So I'll just like talk briefly about semantic segmentation, and we talked about image classification. I have a notebook for you which you can like play with afterwards and do semantic segmentation on any image that you like. But basically, this is a problem where instead of just predicting one class for an image, you predict one class for each pixel. So I think this figure speaks for itself. You want to like exactly label where the cat is and exactly where the grass is and where the trees are and where the sky is and da, right? And you can think of this as a simple, well, not so simple, but at least an extension of the classification problem. In the previous case, you only do one classification. In this case, you do you solve many classification problems. And how many exactly? Basically the product of the height and the width, right? So because every pixel is a classification problem. You take this pixel maybe, and you say, what is this? Is this a sky? Is this a tree? Is this a cat or a grass? So you solve a classification problem there. Then you take this pixel and you do a classification problem there, and so on and so forth, right? So clearly I'll not have time to talk about like the exact details of semantic segmentation, but I have a notebook for you, and it's the same notebook. So it's if the link is on the chat, then you can go there. And I'll show you like an example network being applied on images. And again, you can go after this talk, you can also play with those images, you can try new images and everything. So I've already run this, I've gotten the results for you because it might take a little bit of time because the neural network is still running on the CPU of Google, not a GPU so far. So it might take like just two seconds or so, but you can see the results are pretty cool, right? Like this is a pre-trained network, and you can see how clearly the boundaries of the bike are kind of detected, right? It's not like blurry in any way. Same with the airplane. I mean, these results are actually so good that I wish I could have results where I could show you some mistakes, but they're pretty good. Like maybe in this case, like this red thing is so harsh, but I don't think this is a part of the harsh. But I mean, it's pretty good. So you can see like the state of the art is like really good. And this is something I've just run on a CPU and on very quickly, right? I mean, you can run this on your local machine. This doesn't need like a lot of processing because it's already trained. Training needs processing. So again, if you have more images, or if you want to try this on more links or something, you can add them here or just message them in the chat. And if I have some way of accessing it, I'll, or I mean, if I find a way to access it, then I'll put them here, but you can do this on your own also. I think I'll end here because we are only 2 minutes away. And the topics that I have remaining, those were anyway extra topics, but they'll take quite a bit to go through. So I can take questions, or if, I don't know, Felicia, if you want to give the survey first, whatever.
Yeah, so before we get started onto the Q&A portion, we'd like y'all to take like about 3 minutes to take this short survey for feedback. I'm posting it in the Zoom chat right now. We'd really appreciate that. Okay, hopefully everyone had the time to fill that out, and we can start the Q&A now.
Cool. So I'll take questions from the chat. I don't know if you can also tell me questions in the Slack, Felicia, if there are any. But I think the first question was like, can you use CNNs outside of images, videos, such as for spatial statistics? The answer is yes. The CNNs can be used everywhere. Everywhere when you want to do some sort of local processing, and if you like understand CNNs on a more deeper level, the properties, like if edges or if features that are close together have more meaning than features that are away from each other, like in the case of images, the pixels that are closer have more meaning than pixels that are away for that particular region. CNNs are used. I mean, I have used CNNs for like audio classification or something like that. And they're used in like, I also know there is a paper which uses CNN to predict the number of COVID-19 cases in the future. So there, you can use CNNs, like they're pretty popular. You can use them in a lot of fields. And the other question is, can you explain in general what architecture means in the context of neural networks? Yes. Architecture, by architecture, I basically mean the design of the neural network, right? So if I share the screen again, it's how you organize the layers, right? And I mean, I did not get a chance to talk about future learning, but I will soon, hopefully. And then it's how you organize these layers, right? Who decides where the pooling layer goes, and why does it not go as the second layer? Why the third, right? And all those decisions are like architecture decisions. So this is what I kind of mean by architecture. Feel free to ask follow-up questions if you have any, but I'll keep taking the rest of the questions. So to make classification of images through a CNN model more precise, what is the first advisable tuning approach? Should the kernel be tweaked, or is it a more general approach to tweak the network layers? Okay, so the kernel can never be tweaked, at least if you mean the kernel weights, because those are all learned by the network. If you can decide the initial weights, which is like you have to give the weights, you have to put some weights to begin with, and those can have a large effect on the entire process of learning. In fact, there's a paper which I think is titled "All You Need Is a Good Init," which init for initialization, which talks about the importance of initialization in general, basically. But what is the first advisable tuning approach? Most often, the best networks are the networks which are overly strong. They're like overkill, but they are regularized very well. Regularization is I think maybe I don't know if Josiah will talk about it in his machine learning talk, but regularization refers to like how can you make sure that the training, how can you make sure the testing set performance is not very bad or much worse compared to training set. So it's hard to say one approach works for everything, but like there are ways to do experiments to see if the network is even strong enough for this task. For example, if you have like 1,000 images in your training data, maybe take 20 and learn on 20 images and see if the network gets 100% accuracy in 20. If it does, then it at least is strong enough to get 20 images. Maybe it is strong enough to get 100. But if maybe it is not even strong enough to get 20, then you need to know that you need to add more strength. More strength meaning more parameters, more layers, etc. More questions or follow-up questions, whatever. Feel free to also unmute and just ask. What are some of the regularization techniques, and is there an easy way to implement? Well, you don't, in deep learning, everything is easy to implement because you don't implement it, you just use them in pre-built libraries, right? So common ways of regularization are... Question? Not sure what was that. But yeah, so the first regularization technique is like the L2s, which is called weight decay, basically, right? You say that the weights of the model should be closer to 0. They should not be unnecessarily large if there is no need, which says, without mathematics in English means that you say learn features which are important and ignore the ones that are not that important in some sense. I mean, the best reference for anything deep learning related is that deep learning book that I had, which was, if you just, I think, go deeplearningbook.com, and that has like pretty much a lot of details about everything. But other regularization techniques are include data augmentation. Like, for example, I showed you an image of a cat or a baby maybe, but if you flip that baby 180 degrees, it's still as a baby, right? So, and this is mostly true for most images. I mean, if you have numbers, maybe that's not true, but for many types of images, that's true. So when you train, you also give these flipped images. So the network gets more data. You kind of create more data artificially, right? There are other ways of weight regularization. It's L1 norms, there's a lot of regularization literature. In fact, in that book that I'm talking about, there's a whole chapter on regularization, and it's really wonderful. What was the URL again for deep learning? It was deeplearningbook.com. I think that's right. Let me check. Yeah, deeplearningbook.com. How do you determine good initial weights? There are again many methods that do that for you. Like in many cases, what you do is you just take numbers close to zero, and they usually work fine. But there are like more advanced methods which will like take into account some statistical distributions of your data and then choose weights accordingly, or like make some prior assumptions about it. Mostly you don't, that's not a conscious decision that you make at least when you start as a beginner in deep learning. You will not make that decision consciously. Mostly it will be made for you in like the library that you choose or something. But as you get more advanced, that's like one of the, it is an important thing, but it's like there is no like, I think like just one formula I can tell you this is the way and do it. Sure, yeah, deep learning org, sorry, not com. And more questions? I'll share that slide. I mean, I'll share my screen and so that you can see that future learning slide. And I mean, since I cannot read questions easily when I'm sharing screen, maybe Felicia, you can tell me if there are questions while the screen is being shared.
Sure.
Basically, I just like go through them. This is easy. Like I don't have to keep this on for long. But Stanford CS231 and lectures, which is like the computer vision class with deep learning in Stanford, those are all online, and they are like the most wonderful resources for this, for deep learning in general and for computer vision. And 224N is natural language processing with deep learning. Those are like relatively advanced, but I mean, if you watch them with determination, you get them, I think. And then there's the deep learning book, which it's like the Bible. I mean, it has all the details you need mostly. I mean, it was written in 2015, so from deep learning standards, that's too much. So it won't have like the most recent advances maybe, but like all the concepts are there. And like you can Google them. I don't think you need like the links really. Maybe if I share the slides, you'll get them. More questions?
I don't think there are any more questions, but if y'all have any more questions, feel free to put them in the Slack under the appropriate, it's like in the Ask a Teacher channel in the appropriate thread. But thank you so much for being here, Ankit. I think we can all agree that that was a really great presentation and that we learned a lot from it. And thank you for everyone for coming. Please consider applying to TAMU Datathon if you haven't already, and fill out the survey. I'll put the link to the survey again in the Slack channel for this, in the thread for this presentation. And thank you again, Ankit, and we really appreciate your time here.
Yeah, thank you everyone for coming. I hope you learned something.